Hello everyone. Today I'm going to be recording my presentation on calculating temperature and species concentration from quasi-2D combustion video data using physics-informed neural networks. My name is Benjamin Cohen. I'm with the University of Southern California, and this presentation was given at the Western States section of the Combustion Institute in Salt Lake City, Utah. Let's start with some motivation. Why are we studying quasi-2D combustion? Quasi-2D combustion is prevalent in high aspect ratio systems like car engines. Under these conditions, various instabilities influence the most important factor of any flame, its speed. The flame instabilities in a narrow channel include the thermal expansion instability, buoyancy-driven instability, viscous effects, and diffusive thermal instability. The best way to collect experimental data of quasi-2D combustion is using a Hele-Shaw apparatus. A Hele-Shaw apparatus consists of two parallel plates with a small thickness apart. We call that thickness D. Here is our Hele-Shaw that we have in our lab. It's about 1 meter long by 0.5 meter wide, and we have the ability to vary the cell thickness from 3 to 25 millimeters. Here is a video of a lean-burning dilute hydrogen flame. The video is being played back in real time with an equivalence ratio of 0.4 and a T adiabatic of 1200 Kelvin. Notice the cellular instabilities that form, and notice in the second half we get a nice sawtooth shape. For the purpose of this presentation, we are going to be trying to zoom in and look at the tip of the sawtooth to see if we can get a better picture of what is going on. To capture this effect, we took our camera and we positioned it close up so that our new domain size is videoing over 2 centimeters by 2 centimeters, and we now have a frame rate of 500 frames per second. This is the video that we saw. It's very dim. It's very hard to see the flame. In fact, it is playing. Maybe just turn down the brightness in your room. So the question is, why can we see the first video at 30 frames, but not the second video at 500 frames per second? To answer this question, we need to look at what are we actually seeing. The light emitted is near-infrared light at a band of 823 nanometers, which is being emitted by the hot water vapor. We know that the hot water vapor's light intensity, or radiance, is proportional to an exponential, 1 over the exponential of 1 over our temperature minus 1. We also know from Beer-Lambert's law that the radiance is proportional to the concentration of the water vapor. Together, the temperature and water concentration gives us a function that allows us to map a temperature and concentration profile to brightness. Here's a histogram representing the relative frequency of pixel values compared to a noise video and a signal video. The signal area represents the portion of the video of where the flame is present and the pixel values corresponding to the flame. The noise area is the area under the curve of the pixel values of a video comprised of no flame present, meaning it's just the background radiation. We divide the signal area by the noise area to get a signal-to-noise ratio. For the 30 frame per second video, the signal-to-noise ratio is 2.5. Comparing that to the signal-to-noise ratio of the 500 frame per second video of 0.24, we see the signal-to-noise ratio drop by a factor of 10. Now we can understand why we can see the 30 frame per second video, but not the 500 frame per second video. So the question becomes, how can we do some quick processing to actually see the 500 frame per second video? We are first going to look at our signal-to-noise ratio diagram of our 500 frame per second. We are now only going to look at the area above the noise curve but below the signal curve. We are then going to integrate this curve and normalize the values from 0 to 1. This represents a mapping between 8-bit pixel values to light intensity, 0 being black, 1 being white. This artificially shifts our histogram, resulting in a new signal-to-noise ratio of 2.05. Applying the intensified mapping to our video, we result in this video. We can now clearly see the tip of the sawtooth, however, the video is incredibly noisy. I'm now going to walk us through how we can use physics-informed neural networks to denoise the video into what you see here. First, let's start with our physics setup. A video is simply a mapping from 2D space and time to light intensity. you can select your frame and then select your X pixel and Y pixel value to map to a light intensity, which we call beta. Now we're going to look at a solution to a system of partial differential equations that maps from 2D space and time to temperature T, concentration Y, and velocity V profiles. This formulation was developed by Professor Fernandez-Galisteo, Professor Kurdyumov, and Professor Paul David Ronney. For a quasi 2D reacting flow, we want conservation of mass to be obeyed, conservation of momentum. To simplify, we're going to be using one-step chemistry. With very small velocities, we can neglect convective terms of momentum and invoke Darcy's law. And we also want to obey conservation of energy and conservation of species. First, when solving a system of partial differential equations, we want to go from dimensional terms to non-dimensional terms. Here, we're going to be non-dimensionalizing by the laminar burning velocity, the thermal flame thickness, and the adiabatic flame temperature. We now want to invoke the following equations of state. First, the ideal gas equation, then reduced viscosity law, which are going to be classified by the thermal expansion ratio Q, and we also have our dimensionless rate of fuel consumption. With all of our physics laws shown above, we can now boil these down by using substitution into 3 partial differential equations, which we will attempt to solve. To satisfy the system of 3 partial differential equations, we're going to look at the difference between the left-hand side and the right-hand side to make a residual term, R of t, R of y, and R of p. These residual quantities squared, summed, then integrated over our domain results in a loss function, which we'll call loss of our PDE. This loss function for our 2D reacting flow, when is equal to 0, means our chemistry is satisfied, our conservation of energy, momentum, and mass is satisfied, along with Darcy's law, and our ideal gas law, and our reduced viscosity law. We now have these 3 functions. First, a video that maps space and time to brightness, then our PDE that maps space and time to temperature, concentration, velocity profiles, and then our Planck's law that maps temperature and concentration to brightness values. We now can take our physics model, our system of PDEs, and compose that with our brightness model to get something that resembles our video. We can now look at the difference between our video and our brightness model composed with our physics model to get a residual of our data. We can then integrate this residual over our boundary domain to get a loss for our data. However, there's one issue with this. One, our video data is discrete, and our brightness model and our physics model is continuous. Also, we are looking at relative terms. The way we get around this is by looking at a function that helps with shape recognition. We only want to compare the shape of our video, the shape of the flame in our video, and the shape of the flame from our brightness model. Here is the general formulation that looks at a system of convolutions. And here is 2 videos or 2 photos comparing them with our shape estimator that evaluate to 0. So unlike the L2 norm, where any pair of these photos would not be 0, these 2 images under our shape estimator would evaluate to 0 because these 2 images are the same under our shape comparison function. We're now going to do some neural network review. A neural network is a universal function approximator. The neural network's most simple component is comprised of a neuron. The neuron simply takes a weighted sum of the values of the layer before it and then feeds this through an activation function, ultimately mapping between 0 and 1. The weights of our network are updated using something called backpropagation, where we look at the gradient of our loss with respect to all the weights and then move all the weights in the direction of the gradient, trying to lower the loss function to 0. We now apply Planck's law and Beer-Lampert's law to the output of our neural network to get our full model. Here's the original video, just to show you guys again, that maps space and time to brightness. After training, here is the temperature profile from our model. Here's the concentration profile after training. Here is the velocity profile after training. And here is the brightness model applied to our temperature and concentration profile. One more time, a side-by-side view. To summarize, we were able to decompose video data using a physics model and a brightness model. From this, we constructed a temperature, concentration, and velocity profile. And by applying our brightness model, we reconstructed the noise-free video data. Some of the advantages of this is that we actually have a continuous function instead of a discrete data set, and it's also a very low training cost to perform this. Some of the disadvantages, though, is it is costly to determine the accuracy of the constructed profiles. To compare DNS to pins, the marginal experimental cost is 25 cents for pins. Obviously, there's no experimental cost to run DNS. The computational cost is about 500 times less, and the storage cost is about 100 times less because we're storing a function instead of a discrete data set. In the future, we plan to validate through looking at 3D direct numerical simulation that incorporates detailed chemistry and heat loss. We also want to use a multi-camera array to reconstruct a 3D profile. We also want to try training with a larger domain and obtain a parametric data set so we can train reduced order models. I would like to thank my Ph.D. advisor, Professor Ronney, and I would like to thank Dr. Zhou for mentoring me during the course of my studies. I would also like to thank the Combustion Institute and the University of Utah for hosting this conference. Thank you for watching.